All right, so now we're going to look at an example where we are going to calculate the test statistic for not equally likely items. So let's say you're playing a dice game where you roll 2 dice, and if you roll doubles, you win the grand prize. If you roll numbers that are 1 apart, so that would be like you roll a 1 and a 2, a 3 and a 4, or a 4 and a 5, 5 and a 6, you get a free turn, and anything else is considered a loss. So you think that the dice are weighted, which means they wouldn't be fair dice. So you keep track of the next 40 turns. You found that you won the grand prize 3 times, got a free roll 8 times, and lost 29 times. Using a 0.05 significance level, determine if there's evidence to suggest that the dice are weighted, or essentially that they're not fair. So the first thing we need to do is we need to check our requirements. Okay, so a random sample. Since we are rolling dice and you just keep track of your next 40 terms, that would be considered random. Okay, then we have to check, do we have frequency counts for every single category? Well, we do, because our grand prize we had 3 times, our free roll we had 8 times, and then we lost 29 times. And then our last requirement is the expected frequency for each category at least 5. So here we're going to have to do a little bit more work. Now, if you are not sure about all possible outcomes when rolling 2 dice, you can just look up online or in your textbook, and it will give you a visual display of all possible outcomes when rolling 2 dice. So if you need to look at that, you can. So if I look at my different categories here, if I look at rolling doubles, there are 6 different ways for me to roll doubles. So I would expect there to be 6 out of 36, because there's 36 total outcomes when you roll 2 dice. I would expect 6 out of 36 to produce doubles. Now the 1 apart, there are 10 different ways that can occur. So I would expect 10 out of 36 to result in values that are 1 apart from each other. And then everything else, there's 20 options of everything else, so 20 out of 36. So now when I do my expected value, I have to figure out, well, if 6 out of 36 happen with doubles, how many would I expect if I rolled 40 times? So I would take 6 out of 36 times my 40, and that's going to end up giving me 6.6 repeating. Then I'm going to take my 10 out of 36, because that's the proportion that should be 1 apart. I'm going to multiply that by 40, and that would give me 11.1 repeating. And then my 20 out of 36 is the proportion that should be everything else. Take that times 40, and I would get 22.2 repeating. So for my requirement, it says I have to have at least 5 expected for each category, which I do because none of these values were less than 5. So all of my requirements are met that I can now go on and do my hypothesis test. So I'm going to set up my null hypothesis. Now this one is different than what we did with equally likely, because these have specific values for each category as opposed to all of them being the same. So I just use the notation G for like grand prize. So my proportion that would be the grand prize would be 1 out of 6. That is just the 6 out of 36 reduced. And then my proportion for a free roll would be 5 out of 18, which was our 10 out of 36. And then the proportion for losing ended up being 5 out of 9, which was our 20 out of 36 reduced. So I am looking at, this is my hypothesis, that those are going to be the proportions for each of those categories. Now my alternative is going to be that at least one of the proportion is different from what was stated in the null. So now we're going to go ahead and we're going to compute our test statistic. So we would do our observed values, we need our expected values, we're going to need the difference between them, and then our observed minus our expected squared, and then our observed minus our expected squared divided by our expected. So this is the exact same table that we used to calculate it when we had equally likely outcomes. Okay, so our observed values for the grand prize, according to our problem, it says they won the grand prize 3 times. They had the free roll 8 times. And then they lost 29 times. So those are our observed values. Now our expected values we just computed when we were checking the requirements. So my grand prize, it was expected to be 6.6 repeating. My free roll was 11.1 repeating. And my losing was 22.2 repeating. So those expected values I had already computed when we were checking the requirements. So now when I go ahead and do my subtraction, so for the grand prize I would need to take 3 minus the 6.6, and that's going to give me a negative 3.6. For the free roll I would need to take 8 minus the 11.1, and that'll give me a negative 3.1. And then on my last one I would do 29 minus 22.2, and that's going to give me a 6.8. Now, my next column, I need to square each of those values. Again, at this point, you should have no negatives left after you do this. So these are all my values squared. So I took my observed minus my expected column, squared them to get my new column. And now I need to take this column here, my squared values, and I need to divide them again by their expected value. So here I have each of my squared values here divided by their corresponding expected values, and then the last thing I need to do for my equation is I need to find the sum of that particular column. Now when we go and end up doing this using technology, you will see that our values are going to be slightly off, and that's because I've rounded all of my values. So I found my sum to be 4.906, so that tells me my chi-squared value for my test statistic is 4.906. Now, I would need to go and look up my critical value. So from my chi-squared standardized table, my degrees of freedom, well this time I had 3 categories, grand prize, free spin, or lose. So 3 minus 1 is 2. So when I look up my critical value in my chi-squared table, I get a critical value of 5.991. Now remember, this is only ever a right-tailed test for goodness of fit, so my critical value here is 5.991. My test statistic was 4.9, so I ended up falling in the non-rejection region, which means I do not have evidence to reject this claim. So it appears that the dice are probably not, or I don't have enough evidence to say that the dice are weighted. Okay, now, as you can see, again, doing the hand computation can be pretty time consuming. And there is definitely room for error and rounding errors and those types of things. So what we're going to look at now is how can we do this particular test on StatCrunch. So we would go into our stat menu, goodness of fit, and then the chi-squared test. We're first going to look at the equally likely outcomes using the Skittles example. Then we will look at the not equally likely outcomes, and we'll use the dice game. Alright, so I've opened up StatCrunch here, and I have my categories entered, and I have my observed values entered here. Now, because this one is an equally likely outcomes, I didn't have to enter my expected values because StatCrunch will do that for me. So in order to do my goodness of fit test using StatCrunch, I'm going to go to the stat menu, down to goodness of fit, and then I'm going to choose my chi-squared test. So it asks me to select my observed. Well, as you can see, I titled that column observed. And then for the expected, it gives me the options to either select a column or all cells in equal proportion. Now, since my hypothesis test was testing whether these were equally likely outcomes, I can just select all cells in equal proportion, and it will compute what my expected value is. So I don't actually have to type the expected values into my data sheet here, because Excel will do it for me. So now I can press compute, and it gives me my printout. And as you can see, my test statistic it has computed right there is 0.52564, just like we had before. And then now notice it also does give me my p-value. So depending if you're using the critical value approach, where you would then go to the standard table and look up your critical value, or if you're using your p-value approach, we have both of those right here. Alright, so I'm still in StatCrunch here, and this time I've set it up for the dice problem that we looked at. So I looked at my categories here. I could win the grand prize, I could get a free roll, or I could lose. My observed values were 3, 8, and 29 still. Now on this one, because they are not equally likely, we have to enter our expected values. So I had computed those when I was doing my test of requirements, so now I had to manually enter them in here. And I'm going to change that heading from variable 3 to just expected. That way, when I have my menu up, I know for sure which ones to click on. So again, I'm going to go to Stat, I'm going to go to Goodness of Fit, and I'm going to go to chi-squared. So my observed values are in the observed columns. Now this time, I have to select the column for my expected values because this one is not equally likely. So I would select the expected column, and then I'm going to press compute, and it's going to give me my test statistic. And then again, it's also going to show me my p-value here for this particular one. So we can use the critical value method that we've already talked about, or we can use a p-value method if we would rather do that. So if we look at a summary of what we did, we looked at kind of what does goodness of fit really mean? How can we set up our hypothesis test? So we have to first check our requirements, set up our null and our alternative hypothesis. And remember, sometimes you'll be working with equally likely, and sometimes you'll be working with not equally likely. And then we would work with our test statistic. Now you can either use the critical value method, or you can use the p-value method. And then we also looked at how to do that on StatCrunch to make things a little bit faster. So regardless of what you're working with, you need to always make sure that you can distinguish, is this a goodness of fit test? Is it equally likely or not equally likely? And then which method do you prefer? And make sure that you can interpret your results using whatever method you choose.